right, good morning, my friends. It was quite an adventure getting here. I guess I'll write the blog post, but I'm super happy I made it. It's an honor to be here, and it means a lot to me. And apologies for not speaking Hebrew. I guess I will learn at some point, but if I stick to English, I think I'll get my message across, right? And thank you so much for putting together this amazing event. I'm really, really glad I'm here. So, my name is Julien. I'm the chief evangelist for a startup called RCAI. And in this session, we're going to talk about one thing: small, open source language models, and why they're the number one thing you should be looking at instead of those silly, large, huge, closed models. So I spent a lot of time talking to enterprise customers, right? People who want to build real-life products, real-life applications with AI. And this is the one-slide summary of what they want. Number one is they want maximum privacy, security, and compliance, whether it's the model or the data or their customers' data or personal information that could be in that data. They don't want to share it with anyone else, right? No, we don't train on your data. Well, maybe you don't, maybe you do, but I'm not going to take the chance. The number two thing they want is they want the best model for each use case, right? The Swiss Army knife model that is supposed to work everywhere for every use case, in every industry, with every language, etc. That's a lie, right? And I think by now people have realized it. So they want the best model for the job every time. They want different options. Some use cases are small scale, some use cases are large scale. Some use cases are high ROI, some not so much. Right? So again, the one-size-fits-all model and the one-size-fits-all infrastructure that supports the model is a terrible option. And because these folks have real-life problems in the real-life industry and business that they're in, they need to design for ROI. They're not trying to build stuff just because it's funny or cool or to bump their resume, hopefully. They want to make money or save money with that AI solution, right? So they need to design for ROI. And I'm sorry, but closed models don't deliver, okay? If you don't agree, wait for me after the session and we can yell at each other for 2 hours. But trust me, they don't. Or you can say, oh yeah, you're absolutely right, and we can have a friendly coffee together. No yelling necessary. So I'm sure you've seen this, right? The open source community has been busy over the last couple of years, building better and better models that catch up to the best closed models out there. And Maxime, hopefully, if you're listening, could you please update this, because it stops at July, and we've had quite a few great models since then. And so now it's fair to say you can match or even outperform the largest models out there with open source models that are just a fraction of the size. But these are the baseline models, right? The off-the-shelf general purpose models, which are nice. They're a great starting point. But how can we do better than that? So we do better by adapting the models to our particular use case, our particular problem. And this is probably how you do it today. You start from a pre-trained model, maybe from Hugging Face, apply some additional pre-training to it to inject domain knowledge in financial services or healthcare or any industry you're in. Then you probably run instruction fine-tuning to tweak the Q&A behavior of the model, help the model understand how you want your questions answered. And last but not least, you probably run alignment for tone of voice and safety and generally, again, to teach the model about human preference, right? This is a good answer, this is a better answer, so please answer this way instead. There's nothing particularly wrong with that. A lot of good models, a lot of good customer models are built like that, and we built a lot of good models that way. The papers are out there, the tools, the Hugging Face libraries, everything is out there to let you do that. But that's kind of 2 years ago, so there are a few problems still. Number one, and it's not very often discussed, that would be a good session for me to work on, is building data sets is super difficult. It's a lot of hard work. You need a ton of data if you want to do pre-training. And I'm not even talking about initial training. I'm talking about continuous pre-training. We advise customers to have at least 1 billion tokens. So well, you could say, yeah, it's Israel. We have 100 billion. No big deal. Right? I know you guys. But for a lot of organizations, 1 billion tokens is quite a bit of data to prepare. So not so easy. And for instruction fine-tuning and alignment, you need very good question and answer pairs, right? Because this is really the last round of training you're going to do to the model. So they need to be high quality, they need to be diverse, because different people will ask the same question differently, etc., etc. So it's a fair amount of work. I'm not going to focus on data sets today. We have a library to help you with that. I'll mention it along the way. Today we'll talk more about training, but keep in mind that data sets should not be underestimated. The bigger problem is training or fine-tuning models puts you in a difficult situation where you have to decide whether you want to favor accuracy or cost, which is a horrible decision to make because we want both, right? And the reason for this is because, well, first of all, you can't really fine-tune those closed models. They have fine-tuning APIs. I could talk about them for 10 seconds. But this paper tells you everything you need to know, just came out. How well do commercial fine-tuning APIs infuse knowledge into LLMs? I'll save you the paper. My conclusion is not well at all. And that's the polite way to put it. So let's ignore closed models for now. Let's focus on small language open source models. So you could run full fine-tuning, right? You could fine-tune all the model parameters on your data in the original precision of the model. So let's say 16-bit. Okay, I'm sure a lot of you do that. That's fine, that's not very difficult to do, but because you're tweaking every parameter in the model and because you're using a ton of data, it takes quite a bit of computing power. So you need to go and find those GPU instances somewhere and pay for them, if you can, right? We work with AWS, and we have a lot of interesting discussions on we need more GPUs, find them for us, please. And so most of the time they do. If you look at better techniques, more efficient techniques like parameter efficient fine-tuning, I'm sure you've heard about LoRa and QLoRa. These help. They help you train only a subset of, with only a subset of the memory required, so you can save on GPU memory, you can save time, obviously you save money along the way. And generally this is a good technique for the later stages of the training pipeline, instruction fine-tuning and alignment, right? So that's a good technique. However, for pre-training, and continuous pre-training particularly, there is very significant accuracy degradation. So, to make a long story short, if you're trying to inject domain knowledge in your model using LoRa or QLoRa, you will be very disappointed. So we have a blog post with that. And there is also a very good paper, LoRa versus full fine-tuning, an illusion of equivalence, which I highly recommend. So, how do we fix those challenges? Well, we fix the challenges by implementing new techniques, right? Trying to evolve that training pipeline that we saw. And that's what RC has been doing for the last 18 months. And we introduced a collection of new libraries to help you do the same. So the first technique that we promote is model distillation. And this is implemented in a library called DistillKit. So the intuition is, you saw on this initial slide, we have a lot of really good open source models, right? We have Llama, 400 billion. We have some really amazing models that somebody spent a ton of money training. So thank you, but we're not going to do the same. We're going to take those models, and we're going to teach smaller models to mimic the output. So we'll take the 400 billion model, and we'll train maybe an 8 billion or a 14 billion model to predict as closely as possible as that big model, right? So we have a teacher model. We run inference on a data set. We store the logits, so the raw values coming from the model before activation values. And that becomes our training set. So we train the smaller model on literally predicting like the bigger model, right? And we apply training and we get a distilled model. And I'll talk about spectrum in a minute because that training process can be optimized too. So now we have a teacher model and a student model, and we need to match how they predict, okay? So the loss function for you math heads out there is basically minimizing the difference between the two token distributions, right? And this is done with a fancy function called the Kullback-Leibler divergence. Go and check it out. I'll have a video on that stuff soon if you're interested. But that's completely unnecessary detail for you, right? The intuition is try to predict as closely as possible to the teacher. And this is a simple process. It's just the code is actually very simple. So distillation is nice because we can inherit from the knowledge of a much bigger model. We don't have to train completely from scratch a new model hoping that it's kind of good enough. Now, the second thing is that training process, right? We're stuck between full fine-tuning, which is accurate but expensive, and LoRa, which is not so expensive but inaccurate. So how do we solve that? So we solve that with another technique which is called spectrum, which we introduced a few weeks ago. So the intuition for spectrum, a few months ago, not a few weeks ago, a few months ago. The intuition is that we don't have to train all the layers, right? We need to look for the layers that have the highest contribution to the output. And we'll train only those, but we'll train those in full precision, not in LoRa or QLoRa precision. So there's a little bit of math involved here. Again, I'm not going to go into the math. The key concept is a thing called the signal-to-noise ratio for each model layer. So there's a bit of linear algebra involved, but it's still a very fast process to compute. So we run spectrum, we identify the layers that have the highest signal-to-noise ratio, meaning the highest contribution to the output, and we keep only maybe let's say the top 25% layers, and we train those, right? So when you run spectrum, it will compute the signal-to-noise ratio for each model layer. It takes a few seconds, and it will output a config file that you can inject in your PyTorch code or your other tools to basically freeze all the model layers except the high signal-to-noise ratio layers. And then you will train those with full fine-tuning and full precision, right? And spectrum outperforms, LoRa, QLoRa on every benchmark I've seen in terms of accuracy. It gets very close in terms of memory saving, and it's pretty much a match for full fine-tuning at a fraction of the cost. So if you haven't looked at spectrum at all and you're still doing full fine-tuning, or you're frustrated with LoRa, I highly recommend looking at spectrum. It's very easy to implement, and you will save quite a bit of time and money without degrading accuracy, right? And yes, I have a video on this one as well. Okay, how do we keep improving this? Model merging. Who has heard of model merging? Okay, a few people. All right, good. So model merging is another interesting technique where we recognize the fact that we have a ton of good models out there, right? Hugging Face has 1 million plus models. Do you really need to train another one or fine-tune another one from scratch? Maybe, maybe not. So if we have all those great models out there, can we build the one we need by simply merging existing models? Maybe from Hugging Face, or maybe some models we've built before? Maybe we can. So merging is exactly what the name says. It's just a mathematical operation where we, average out the models. So think, model A plus model B plus model C divided by 3. That's pretty much what we do, although it gets a little more clever than that. So we combine multiple task-specific models, I'll show you an example in a minute, into a single model that can do all those things, hopefully better. So it's not an assembling technique. There's only one model in the end. You can run this on CPU. In fact, I'm going to run a demo on my laptop right now. And at the end of the day, you get one model, no inference penalty, and it's super nice, right? So merging is exactly this. We take model A, model B, model C. Ideally, they would have the same architecture. It makes it easier, but you can do heterogeneous merging if we want to. And then we run merge-kit for a few minutes, and we get a merge model. So the reason why it's working, and this is by no means a scientific explanation, is if you imagine the embedding space for the different models. Imagine you have a math model, and you have a code model, and you have a Hebrew model. Obviously, there's got to be some overlap between those embedding spaces. But if you pick the models well, they wouldn't overlap so much. So when you merge them, you actually add new embeddings to the same space, as we see here. So you kind of build a model that has the combined knowledge of the original models that you used, right? That's my intuition. If you want to go and read the code, you can go and read the code. So let me show you how this works. So clone the library, install it, job done. Write a config file. So here I'm merging 3 Llama 3, 8 billion parameter models with different weights, right? You can see the math coder is 60%, the SQL coder, which is a SQL model, 20%, and the Code Llama model, 20%. Okay, so it's pretty much averaging those out. That's my config file. Okay, so now how about we run this? Can you read it? Yes. Okay, so no cheating, right? So let's just go and run this. And this is local on my Mac, okay? I'm not using a $100 an hour AWS instance. So I've already downloaded the models. Okay, so start thinking how long it's going to take. I have 17 minutes left, just to give you a hint. Ooh. Can we do under a minute? While we're waiting, imagine how much time and effort you would need to build that fancy math and code model using data sets that you may not even have. Wow, looks like we're going to do under a minute. Come on. Keep going. And then, of course, we'll look at the results. Ah, come on. Usually it's 107. Let's see how deterministic this is. Okay, all right, close. Okay, 108. So 1 minute, so 68 seconds. We built a merged model. Good. On this Mac. So now, I scored the 3 original models on a benchmark called GSM8K, which is a math benchmark. You can see the scores for the individual models. The merge model is 7362. So it's better than all 3 combined, which is quite interesting because it shows if you take math models and inject code models, they become better math models, right? And that improvement in almost 1+% of accuracy is huge. I mean, if you build models for a living, you know. Getting an extra % of accuracy on this kind of benchmark is a lot of effort usually, right? How much effort did it take here? writing this config file, 20 seconds, running this, 1 minute and 8 seconds, right? That's near infinite ROI if you ask me, okay? If you want to know more about the different techniques for model merging, 2 hours of videos on my YouTube channel. So now, let's revisit our training pipeline again, okay? We can be super efficient. We have the same steps, pre-training, continuous instruction fine-tuning, alignment, etc., etc. So if we look at the top, all the training steps, we could use Spectrum, right? We could use Spectrum and save, I don't know, maybe 50% at least on the training time. So we could still do it like that. But if we want to get fancy, we could use MergeKit at every step of the way, just like I did. Some models are strictly built with MergeKit, right? We sometimes build customer models only with MergeKit. So that's good ROI for us as well, but don't tell customers, right? You can merge for domain knowledge. You can merge for Q&A behavior. You can merge for alignment. Or you can combine, right? Let's say you have some super fancy, super confidential company data. You could still run pre-training with Spectrum to inject the data and the knowledge into the model. You wouldn't find an existing model for that. But then, for Q&A and alignment, you could use some, open source data sets and fine-tune that way, right? And run MergeKit instead of fine-tuning, actually. So all those combinations work. And for data sets, to help you build better, richer, more diverse data sets, we have another library, which I mentioned earlier, which is called EventHandler, which basically will start from your existing data set and using some clever prompts and a large model on the side will generate better prompts and better answers. So if you have dataset problems, go and look at EventHandler. So that's the foundational technology that we've been building for a while. And to prove our point, and as we know, the proof is in the hummus. Yes, I need to, adapt myself here. Well, we use our stack to build models, and we put them on Hugging Face. So we built a 1.5 billion parameter model called RC Lite. It was the #1 in its class when it was released. We built an 8 billion model. It was the #1 when it was released. We built a 14 billion model. Guess what? It was the best when it was released. We built the best Arabic model. This one is not on Hugging Face, it's for customers, right? If everybody wants to build the best Hebrew model, come and talk to me. And we built the best 70 billion parameter model, okay? And why are they the best on those Hugging Face leaderboards? Because of everything I said before. Because you can't just train and build models the way you built them 2 years ago. You need to be more clever, and you need to go and use the fancier techniques. So just to show you how we built Supernova, the 70 billion model. So we started from the big llama, 405 billion, and we distilled it, okay? And you can see it took, 32 H100s for 5 days. So not the cheapest thing, but it's nowhere near the cost of training a new model completely from scratch, which you cannot do unless you're Meta or Microsoft and have billions of VC money to burn before Christmas. Then we took Llama 3.1 70B. We built a really nice data set with EventHandler, and we applied Spectrum training to it, and that gave us another 70B model. And then we took the original Llama 3.1 70B, we run alignment on our own data sets, and that gave us a third model. And you know what's coming next, because we want one model, we don't want 3. We merged them in a clever way, and that gave us Supernova. And Supernova, on the IF-eval benchmark, outperforms Llama 3.405B, it outperforms Claude 3.5 Sonnet, and it outperforms GPT-4o. And that's not even the best model we have. We have some better ones right now. Okay, so how does a company like us, about 40 people, bunch of geeks, how do we build a model at reasonable cost that outperforms the monsters from the Silicon Valley? Because of the training pipeline. So it never stops, right? So just to show you, maybe a week ago, we released Virtuoso Small, which is part of the model engine that we just built. I'll talk about that in a minute. So Virtuoso Small is a 14 billion model, right? Just released weeks ago. And you can see some of our other open source models, the 8B, the 14B, and the 72B. You can see two things here. You can compare Supernova Medius, which was released 2 months ago, to Virtuoso Small, which was just released. Look at the gap in performance. 2 months. Okay? Amazing results on all the benchmarks. Now look at how close Virtuoso Small, 14 billion, is getting to our original 72B model, which was released in July, so not even 6 months ago. So 14B is not quite the new 72B, but give us a few more weeks, right? So if you're working with large models from a year ago or 6 months ago, you can get the same performance today with a model a fraction of the size and a fraction of the cost. Again, because the pace of innovation by RC and generally by the open source company is absolutely, the open source community, is absolutely insane, right? And you can go and compare those to the closed models, but I can't be bothered. So we keep building models, and just a couple of weeks ago at AWS reInvent, actually, we announced our new inference platform, which is called RC Model Engine. I'm going to show it to you in a second. At the moment, we have 6 models. So we have the Virtuosos, which are general purpose SLMs. They come in 3 sizes. We have 2 coding models, and we have a function calling model. Okay? And you can use those, pay per token, APIs, and all that good stuff. So why don't I show you? And yeah, there's a YouTube video for it. I should have a t-shirt that says that. Okay, let me show you. Whoops, where are my glasses? Here they are. Okay, so, that's what it is. All right, there we go. Okay, so you can use the sandbox. You can try the models there. Hopefully Wi-Fi is not going to let me down now. Hummus. See? That's all you needed to know? Yes? That's the best model in the world. It's the proof. Although shawarma and falafel are good too, right? So you have APIs. You can use the OpenAI API to call the models. You can do curl. You can do Python. I mean, the usual stuff, right? So let me show you maybe a better example. Here I'm going to use the function calling model. Okay, so create an OpenAI. Can you read it? Yeah. OpenAI client. And I'm going to call the Yahoo Finance API to get things done. So, get the stock price, get the CEO name, get the company summary, etc., etc. I'm going to define those tools according to the OpenAI function calling spec, okay? So function names, parameters, etc., etc. Then I'm going to define a function that invokes my model, again with the OpenAI API, passing the tools, and checking if there's a function call to be made, and calling the function. Okay, so let's go and try this one. Yeah, let's answer this super important question. Okay, what's the last price of Chipotle? Call the model. So we're going to call the model. We see the model decides to call the getStockPrice function. And then it's going to call that function at Yahoo and return the stock price. Oh, delisted. No. Has Chipotle gone bankrupt? Okay. How is that possible? Okay, I'm sure McDonald's still exists. Let's try McDonald's. Okay, there we go. Right? So here it's one call to the model, call the right, return the right function, invoke the function locally, call the Yahoo API, get the result. Okay? But you may want to do things a little more complicated. So maybe let's do, I don't know, this one. And this time I'm going to call the model, try to invoke the tools, but maybe there's no tool to answer that question. So I'm going to take the result and pass it back. Oh, there we go. No response. No. And we're going to pass the result. Okay, so no response from the tool. Okay, something's broken, obviously. And then we could pass the answer back to the original model and say, well, if you don't get an answer from this, then give me the answer with your own data. Not sure what's going wrong here. Okay, no worries. So you can see here, you know, and this is a 14 or 32, I forgot, parameter model. We can see actually. Here it is. Yeah. 30K context. And yeah, this is a 70 billion because it's a large one. And you can use them just like that. Okay, let's go back to this. So, as a conclusion, I hope by now, almost 2025, people realize that there is no model to rule them all. You know, you tried, you figured it out. There is no model that works across all industries, all use cases, all languages, etc. You need for each project and each use case to find the right use case. So what our customers tell us is that they get more, you know, they get better results, they get more accuracy, and certainly more ROI from small language models, right? They just make more sense. If you need to build a model for your use case, if you need to adapt a model for your company, your data, please look at all those new techniques like EvolKit and Spectrum, and you know, maybe distillation and maybe merging, etc. Because they really completely change the game on cost and time to production and model accuracy. And they're not difficult to use. And for inference, and that's what we're building at the moment, we're testing it with customers right now. We see extreme performance by combining small language models and agents, which could be, you know, integrating with, I don't know, Slack and Jira and Salesforce, etc., or which could be calling your internal APIs. So SLM-based agent workflows are amazing, absolutely amazing. And in a few weeks, we'll be launching our platform for this. It's going to be called RC Orchestra. It will be based on some of the models you just saw in the model engine and some new ones. And I think, and it's drag and drop and no code and all the good stuff. So keep your eye out for this. It's going to be interesting. And obviously, feel free to visit RC to learn how to build all of this. This QR code is a link to our newsletter if you want to stay in touch. So please go and do that. And again, I want to thank you very, very much for having me today. Again, it means a lot to me to be here. Thank you for the amazing conference, and enjoy the rest of your day. Thank you very much.